Hello everyone, your Dr. Zia Tahir here. This video tutorial is vibration analysis of cantilever beam with tip mass in Abaqus CAE. So analysis for natural frequencies and mode shapes of a cantilever beam with a mass attached at its free end is performed in this video. So a steel cantilever beam carrying a mass at its free end, so that end is clamped. So length, width, and depth of the beam is 0.4064, 25.4 millimeter, 3.175 millimeter, respectively, and a steel cube. This cube is attached, firmly attached with free end, and the dimension of the cube is 25.4 millimeter. Modulus of elasticity, Poisson's ratio, and density of steel is taken as 210 gigapascal, 0.37850 respectively. So the required is natural frequency and mode shape for first three modes of vibration, and to compare numerical results which you got from Abaqus, need to compare with analytical results. There are three steps of modeling and analysis in Abaqus CAE. So modeling, analysis, and visualization of results. And here are the steps for modeling and then analysis and then finally to get results. So I'm going to follow these steps for vibration analysis. So first thing first, there's no defined units in Abaqus CAE. So you have to set your own units. So set of units you can use as Newton meter Pascal or pound inch psi or Newton millimeter megapascal. Okay, so I am going to use set one of units, forces in Newton, then dimensions in meters, and stresses or modulus of elasticity in pascals. So you need to first set work directory. So is a folder where you want to save all CAE files and ODB files. So here file set work directory, and then I am going to set a work directory. Okay. The next one need to save model. So file, save that model. So I'm going to save it as cantilever beam 3D underscore mass. So that is model saved. So now in the modeling, first step is to create part and is a 3D deformable solid extrusion. So here in the model tree, double click on parts or click here. So that is part 3D deformable solid extrusion, and approximate size I am taking double of the length, so which is about 1. So now need to draw cross section of the beam, and the cross section of the beam is 25.4 into 10 to raise per 3 and 3.175 into 10 to raise per 3. So breadth or width of the beam is 25.4 millimeter and its depth is 3.175 millimeter. So here create triangles. So that is a triangle with like any triangle, and then here add dimension. So its width is 25.4 e power minus 3, and its depth is 3.175 e power minus 3. So that is a cross section. So I can drag that around somewhere near the center. Okay, so like this way, it is not approximately around the center or here. Okay, so now then cancel procedure. So here you can, with this one, you can edit dimension value if you need to edit it. Here, edit dimension value if you want to. Okay, so done. And then depth. It's a blind. So depth is equal to the length of the beam, so which is 0.4064 meters. So now that beam is being drawn. So this is a beam drawn, and the next one you need to add mass on top of it. So next step is to create a solid extrude and select plane for extrusion and then sketch. And for this purpose, here in the part module, here is the create solid extrude. And it says select a plane for solid extrusion. So that is the plane. And then it says that select an edge which appear vertical and on right. So this one, I'm going to select that edge which will appear vertical and right. And now I'm going to draw that cube here. So again, it's very simple, starting from this point, then adding dimension 25.4 e raised power minus 3, and then this dimension 25.4 e raised power minus 3. So it is perfectly on top of it. And then cancel procedure, done. And then here it is showing its dimension. So it is going upwards. So like as, and here you can change its direction, but I want to extrude it upward. So it is 25.4 e raised power minus 3. And okay, so now that is the like mass which is attached at the end, that is being modeled. So next two steps, create Datum plane and create partition. So these two steps are not necessary, but I'm going to do these ones to make mesh smooth. So create Datum plane, and for that need to go tool, Datum plane, offset from a plane or 3 points. So while in the part module, go to tools, and here is Datum, and it says Datum point axis plane. I'm going for plane. So you can select that 3 point. So these selecting 3 point, and you can see that there is a plane. Okay, or otherwise offset from any plane, you can go for that one as well, or offset from principal plane, so you can choose any of the choice. Next step is create partition, and for that go to tool, partition, face, using Datum plane. So here you can see that in the part features, so there is a Datum plane 1. You can rename that Datum plane as of your choice. So tools, go to partition, and then partition face, and using Datum plane. And it says that select faces to partition. So I am going to select whole of this part, done. And now it says select a Datum plane. So a Datum plane is selected, and then now the partition has been created. Here you can see that. So now these edges, they are different. So in this way, partition has been created. Next step, in the property module, create material, and for material, need to add density in general, and need to add modulus of elasticity and Poisson's ratio in mechanical elasticity elastic. So here in the property module, that is the material. So I am going to name it as steel. So general density 7850 is the density, and then, sorry, double click on that, and then mechanical elasticity, elastic. Modulus of elasticity is 210 e raised power 9, and Poisson's ratio is 0.3. Okay, so now you can see that density is 7850, and in elastic, modulus of elasticity and Poisson's ratio are there. So now here steel material is. Next step in the property module, create section, and the section is solid homogeneous, and then assign section. So in the here in the property module, so that is the create section, or otherwise you can double click here, create section. Section is solid homogeneous, continue, okay, and then here you can assign section, or here you can double click section assignment. So it says that select the region to assign section. So that is the region done, and then section assigned, and now it turned to green. Next step is mesh. So seed part first by size of 2.5 millimeter, and then mesh part assign element type. So here is seed part. So 2.5 e power minus 3. Okay, and then here is the mesh, and then here mesh part. It says the assign addition cannot be meshed automatically using the assign element type. So default is hexagon, and then I'm going to change it to tetrahedron, and then it will assign mesh. Okay, and then here assign element type. So default it is C3D10, so I am going to use the same one. Next step is assembly, create instance, and here you have assembly. Okay, so double click on instance and select OK. So now that part 1 is gone into assembly now. So next step is to create step, linear perturbation, frequency. I'm going to rename it as model. Eigensolver is length source, and then eigenvalues requested, I'm going to request 5. So for that one, here you can go into step module and then create step. So step 1, I am going to say it as a model. Then here linear perturbation, frequency, continue, and then eigensolver is length loss, and then the values requested they are, so number of eigen values requested, so that is 5. Okay, so now the step has been created here, and that's the model. Next step is to create boundary condition using displacement, rotation, and step as initial. So the boundary condition here need to use fixed. So you can go here in the load and then create boundary condition, or double click here boundary condition. So step is initial, displacement, rotation, and select that phase, done, and then all are fixed, all are set to 0, so, excuse me. So that is now boundary condition is being fixed. Next step in the analysis need to create job, perform data check, and then submit. In the meanwhile, I have named this model as Cantilever Beam 3D underscore mass. So I'm going to create a job with the same name, continue, leave everything as it is, and then submit for data check. So data check is completed without any error. So I'm going to submit it. Okay, so it will take some time to finish. So now this job is being completed. So analysis is done, and the rest is all post processing. Next step is in the results visualization for natural frequencies and mod shapes. So right click on and then go to results, and then in the results we'll have like that is undeformed shape, but I'm going for here like plot contour on the undeformed shape, and I am going to do that both deformed and undeformed. So that is the first mode, and its frequency is 9.5192 for the first mode. And remember, we are interested only in YZ plane. Okay, so that is the first mode in YZ plane, and that is the second mode. The second mode is not in YZ plane. Okay, so that is not a mode of interest. Then the third mode is in YZ plane. That is the third mode. And then this is the fourth mode. Again, is not of interest. And then is the fifth mode that is of interest. Okay, because that one is primarily in here you can see. So that is fourth mode is not required, and then second mode is not required. So then natural frequency for first mode is 9.512, and that is about half quarter of wave, and then it is half wave, 2 quarters, and then it 80.004, that is the natural frequency, and then this is about a wave, and natural frequency is 235.82. So these are three net modes, shapes, and then associated frequency. So last step is comparison with analytical results. So analytical results for this type of problem is not that very well established. So I have one chapter from the book, that is Appendix C, Modal Analysis using Uniform Cantilever with Tip Mass, and so lambda omega, that is the natural frequency in radian per second, m mass L raised by 4 over EI, and lambda is a solution of our roots of C18. So that is the equation, or that is equation in matrix form. So here this IT is moment of inertia of attached mass, and MT is mass, which is tip mass attached. So the solution of this equation C18, so that will give different values of lambda. So starting, uh, obviously the first root will be 0, so need to ignore that, and then all non-zero positive roots of this equation, they will give values of lambda. And then that value of lambda is being substituted in C11 to get natural frequency. So this is one of the chapter, and then recently this one is revisit on free vibration of a cantilever beam with an asymmetric attached tip mass, and the approximate analytical solution of first order natural frequency of cantilever with tip mass is given by, so that is an expression. So here EI, length of beam, and then here M is that tip mass which is attached. So that only gives first natural frequency. So in this paper, they solve it using separation of variable, method of separating variable, like separation of variable, and then Laplace transform. So here they have mathematical model, method of separating variables, and then method of separating variables. For that one, here they got omega in terms of lambda, and lambda again is equation 22 or 23. So here capital omega 1 1, so that equation, and these are the values of omega. So once this equation is solved, So then non-zero values, positive values of lambda calculated and then substituted in this equation to find natural frequency. So I have done that in MATLAB. Here is that is the fundamental natural frequency of cantilever beam with tip mass. And here from this paper, so that one, equation 60, equation 60 of that revisit on the free natural vibration of cantilever beam with a symmetric attached tip mass. So when I run that one for all the value, so the natural frequency comes as 9.2246. So 9.2246 is the first mode. And then I created a script using that appendix C, like solving C18 for various values. So for lambda, and then C19, so that will give mod shape. So I haven't got that mod shapes like script for that. So here natural frequencies of cantilever with tip mass. So I got first natural frequency as 9.2, second as 77, third as 236. And then I solved here for this one, this paper for method of separating variables. So for that one, I got first natural frequency as 10.677. So analytical results, the first natural frequency is 9.21, and from the abacus, the first one is around 9.5. The analytical one, the second one is 77.2, and abacus gave the second as 80. And then the analytical third one is 236, and abacus gave as 235.82. So these results are somehow they are a good agreement with analytical results. So comparison with analytical results is done. So then you can use C19 equation for those certain values of lambda. So you can plot mod shape like that eigenfunction phi versus x or versus the length for various values of lambda. So that's all like comparison. So now finally the summary of this video tutorial. So it is a vibration analysis of cantilever beam with tip mass. So first I model uh, beam and using these steps create part and then create solid extrude, create datum plane, create partition, create material, create section, mesh, instance step and boundary condition. Remember that these two steps create datum plane and partition, they are not necessary. So if you will not do that one, so then you will get approximately same results but not that good mesh, like smooth mesh, so you will not able to get. Okay, and then I performed submit the job, and then I get that natural frequencies and mod shape, and finally I compared natural frequencies and mod shapes with analytical results. So the analytical results are like appendix B, model analysis of uniform cantilever beam with tip mass, and that is from the book Piezoelectric Energy Harvesting. So this is from the book first edition, is published by John Wiley and Son, and then the other one is compared with the research article revisit of free vibration of a cantilever beam with an asymmetry attached tip mass. So I hope you like this video. Thank you very much for watching. Goodbye.